In this video, we're going to be looking at this idea that mechanical energy is conserved and how that's going to work, and actually how that's going to work for us. This idea of mechanical energy, first of all, mechanical energy. We use a symbol capital E for this, and you might think that E applies to all forms of energy. Really, it is kind of specific, just mechanical, and you'll see what this means here. What we say is that the mechanical energy is equal to the sum of the amount of kinetic energy and the amount of potential energy of a system. So the potential energy is typically, it's a way of stored energy, but stored because of an object's position or the positions of multiple objects relative to each other. Might also be stored in a spring, as we're dealing with pretty frequently. Kinetic energy, of course, is the energy of motion. And so the sum is equal to what we call mechanical energy. Now, the interesting thing about mechanical energy here that you want to keep in mind, mechanical energy is conserved. In other words, when it's conserved, we say that it's constant. It doesn't change. But there's always a but here. This is in systems that involve only conservative forces. So here we see why we wanted to look at the distinction between conservative and non-conservative forces. So there's a little therefore we can say, with this statement in mind, in systems that have friction, and we all know, this really is every system. There's probably some friction whenever there are parts moving against each other, or objects sliding, or whatever it might be. Then in systems like this, where friction exists, we know friction is a non-conservative force, then E, in other words, mechanical energy, will not be conserved. It will not be constant. Okay. So this matters a lot. We know that the work done by gravity is independent of the pathway. We know that the work done by a spring is conservative work. Spring force is a conservative force. And we know that friction is non-conservative. If you take a different pathway, the friction is going to be a different value. The work done by friction will be a different value depending on the pathway you take. Non-conservative force there. And when non-conservative forces are in play, mechanical energy is not conserved. So when we deal with systems like this, when we deal with this idea of mechanical energy being constant, being conserved, we're really dealing with ideal situations, frictionless. No air resistance, no friction, those types of things. All right. Now I want you to recall two different ideas from some recent videos. And one of the ideas is from Chapter 7. It's the work energy theorem. And the work energy theorem says that the total work done is going to be equal to the change in kinetic energy of a system. So total work is the sum of all the works done by all the forces acting on a system. And if the sum of all those works leads to some net amount of work being done, then it's going to change the kinetic energy of that system. Okay, well, we know that a delta K is equal to a final K minus an initial K. We're going to come back to that. Now we also recall, the other idea that I want to recall here is this idea of work done by conservative forces. Work done by conservative forces. Well, if there are only conservative forces involved, in other words, where a system where mechanical energy is conserved, then the work done by conservative forces is going to be equal to the total work. Okay, that's kind of handy for us. Now, but there's something about this work done by conservative forces. We know that what this is going to be equal to is the opposite of the change in potential energy. So if we do work on the system, then we're going to be actually adding stored energy to that system. So this is equal to an initial minus a final. It's the opposite of a final minus initial. It's the opposite of the delta. So keep in mind that the F and the I are flipped. All right. Well, we can put these two together for us because we see this connection right here. So check this out. Page 2. From those previous two statements, we have this, and we know that the work done by conservative forces is equal to the opposite of the change in potential energy. We know that the total work done is going to equal a change in kinetic energy. All right. Well, the opposite of this, delta U is just a final U minus initial U. So the opposite of that is going to be our initial minus our final potential energies. The change in kinetic energy is going to equal the final kinetic energy minus the initial kinetic energy. And what's interesting is we're going to end up coming back to this basic statement about total mechanical energy here. I'm showing you my notes instead of the more nicely done version here. That's fine. It'll work out. So we're going to rearrange this just a little bit. We're going to be able to say, all right, if I'm going to have just kind of account for all of my initial information on one side, I'm going to be able to say, well, there's my initial potential energy, and I'm going to bring my initial kinetic energy over to the side, which means I have to add it. And I have my final kinetic energy. All my final information is going to be over here, final, and then I'm going to have to add final potential energy to the side. And so coming back to this idea, where the sum of kinetic and potential energies gives us the total mechanical energy, well, what I have here is the total initial mechanical energy. And here I've got the total final mechanical energy. And this is a pretty neat idea. Not only neat, it's elegant, but also extremely powerful. This is going to be huge for us. Whenever we see in science, any kind of science, where something is conserved, there's a law of conservation of something or other, it is very foundational to so much work that is done in science, and especially with this for us in physics. We see that the mechanical energy is constant as long as there are no non-conservative forces involved. So that's supremely important to understand. Now, what I want to do next is take a look at an example. And what this looks like. It turns out with this idea, let me check this out. With this idea of the initial and the final being equal to each other, the total mechanical energy is constant. We're going to see in situations where it's really just simple accounting. If you have something happen over here, you have to have an equivalent thing happening over here to maintain equality. So here's what that's going to look like in our example. Let's look at a classic situation here. Look at a roller coaster. Who doesn't like roller coasters? I don't know. Now, the track of the roller coaster is going to be it's built above the ground level. And we can start with the roller coaster train or car up at this level, and we'll consider the next situation where it's down here and what's changed in between. So we can identify a few things here. We know that there's going to be some velocity right here. We know that there's going to be a new velocity here at the bottom of the hill, or at this new location. We know that this location is a certain distance above our ground level. And we know that this location is a different distance. So there's our final. This car is going to have, let's just call it mass M. Okay. And we're going to ask ourselves kind of an important question. Can we find an expression for final velocity in terms of other variables? And I bet we can. Okay, so there's our goal, right? Now, before we get into just working that out, let's just list out some of our initial and final conditions. What do we know? So initially, we have an initial height, we have an initial velocity. This car on the track has mass, m. Based on these values, it is moving, so this has some initial kinetic energy. And we know that this initial kinetic energy is equal to 1/2 mvi squared. This also has some initial potential energy based on its position, gravitational potential energy. So there's an initial amount of stored energy here, and since it's gravitational, we know the value is going to be mg times the height above some reference level. Now we're using ground level as our reference level, and that's fine. Remember, we get to pick whatever reference level we want, and it doesn't affect our result as long as we're consistent with that reference level throughout the entire problem. So, well, if we know our initial and kinetic and our initial potential energy, we also know our initial total mechanical energy, and it's simply the sum of those two. Awesome. We also understand some corresponding final conditions. Let me list those here. There is a final velocity, final position. There is also a final velocity. The car still has mass m. That hasn't changed. There is a final kinetic energy, 1/2 mv final squared. There is a final potential energy. And since it's gravitational, remember we're still looking at gravitational potential energy, that amount of stored energy. This would be m times g times the final position here, or final height. And the final thing we could say is something about the total mechanical energy. It's the sum of kinetic and potential. Sum of total mechanical energy is the sum of kinetic and potential energies. Okay. So remember our goal. We are looking for some expression for final velocity, for the velocity at this new lower position. So what's going on with that? What can we do here? Well, if we are looking at an ideal situation where there is no friction, then there are only conservative forces, and we know that the mechanical energy will be conserved. And that is huge. This is such a big deal that we can do this. So I'm just simply going to say, I'm going to look at my final is going to equal my initial. It's constant. So I can break this down. This final is my final kinetic plus my final potential, and this is my initial kinetic plus my initial potential. And I know expressions for each one of these components here. I'm going to switch pens. This one writes a little finer. Kinetic energy in the final position, 1/2 m v final squared. The potential energy in the final position, mg times that final height. And my initial kinetic energy, 1/2 m v initial squared. and my initial potential energy, mg times my initial height. So recall, though, what it is we're looking for. We want to find an expression for our final velocity. This is our goal right here. So we're going to do what we can to rearrange, maybe cancel some things out. In fact, right away, I see something pretty cool. Every one of these terms has mass in it, and therefore mass goes away. What's happening here is going to be independent of mass. Hey, that's pretty cool. All right. Now, still going to look at some things. I know that essentially I'm going to have to subtract this business from both sides and start to isolate VF. So that's supposed to be enough. Sorry. Remember, the m's have canceled out, so I'm going to stop writing them. And here I have, and I'm going to be subtracting g. Well, here we go. All right. I also need to multiply both sides by 2 to get rid of that 1/2. Squared. And multiplying by 2, that half cancels. Yeah, squared plus. Now, I'm going to put a 2 here. Okay. 2IF. And, you know, I can factor out the g, and something is interesting that's going to happen here. 2g. Factor out the g. So what I have is y initial minus y final. But y initial minus y final is equal to the opposite of the change in y position. So that's kind of cool. So I'm just going to do a quick substitution, because quite often I'm looking at a change in y, and that's always a final minus initial. Here I've got initial minus final. So I flip it by making sure I understand that this is equal to the opposite of that. So I'm going to have a minus sign in here, and I can just kind of factor that minus sign, 2g, and then I will have final minus initial, which is delta y. And just bring this down. Wow, holy cow. Okay. Now, something interesting, you might say to yourself, whoa, wait. Look what's happening. We expect final velocity to be greater than initial velocity. But you're taking away something here from initial velocity. Won't final velocity be a lower value? And the answer is no. And the reason is there's something very important happening with this delta y. Remember that the delta y is going to be a negative change in value here. Final minus initial, we're taking this small value, subtracting a large value. This delta y will have a negative value, and it will be taken care of by this minus sign, and therefore we are actually going to increase the value of our initial velocity, not decrease it. So it does work out. It's not a problem. And the final thing I have to take care of here is I don't have final velocity by itself. I want my final expression for final velocity. So square root of all this business. There we go. There is my expression for the final velocity of that roller coaster car. And we saw some interesting things taking place. I mean, clearly this equation is one of your big five, one of your equations from kinematics. But look how we were able to get to it. We were able to see that it essentially comes from conservation of energy, which is pretty cool. We are moving into more abstract ideas here. Energy, it's very hard to see energy sometimes. Yes, you can see motion, and we have equations to describe motion. From that, we can start to describe why the motion exists or why it is changing. Then that's why Newton talked about forces. But this idea of energy is something that's more removed from things we can directly observe, and it's sometimes hidden. But also, what we're going to see if we take a look at this level of our work, we're going to see that a lot of the time, if we put our reference level, remember this reference level here is baseline, if we put this in a certain location, then certain terms in this level of the equation are going to end up going to zero. And that's going to be pretty slick for us. It actually makes our work easier. It simplifies the equations. And you'll see that in some of the examples in later work that we do. Thanks for watching.